Hello, this video is going to be a quick guide about Gaussian elimination. I won't go in detail about the math or anything like that, I just want to explain the general principles behind it and how to use it. So what is Gaussian elimination? It's a method for solving systems of linear equations. And a requirement for it to work is that you must have an equal number of equations and unknown variables. If you decide to implement it as an algorithm, its big O complexity will be n cubed. So let's take a use case example. You're given three linear equations and you're asked to find x, y, and z. How do you do this using Gaussian elimination? Well, first of all, you need to know some prerequisites. First of all, you need to know about matrix form. If you have the system of linear equations, you can convert it into a matrix form like this. And you will notice that if you multiply these matrices out, you will return back to this equation form. And you need to know that this matrix form right here is just a shorthand notice to describe this matrix. The other prerequisite is row operations. When you have it in matrix form, what you can do is you can take, for example, this row 3 and add it to the first row. So in this case, we take the third row, add it to the first row, minus 50 plus 100, still minus 50, 50, 10 plus 10, 20, 30, 10, 40, 4,000, 4,000, 8,000. What you also can do is that you can take a row and multiply it by some constant. So for example here, we multiply the first row by 1/2. And as long as all constants in this row are affected, it should be fine. You can also subtract. For example here, we subtract the first row from the second row. And we do it twice, leading to this. So the goal for Gaussian elimination is to essentially remove the lower triangular of any given matrix using these row operations. So for example, if our A matrix is a 3 by 3, as we see right here, we want to have these three zeros. So let's go to our use case. Now how to do this just takes practice, but this was the way I solved this one. So here I took the second row and subtracted from the third row. Then I took the first row and added it to the second row. And now you will notice that we already have two zeros. We are already almost there. I took the second row, multiplied it by 2, and then subtracted the first row from the second row. And now we have our lower triangular. Now, you might be asking, didn't we just switch some numbers around? What is the trick here? The trick is that if we return this to equation form, you will notice that we get something like this. And what you will see is that if we take the lowest equation, it will only depend on one variable, z. And since it only depends on one variable, we can isolate z and figure out what z is rather easily. What you also will notice is that if we go to the equation above, so in the second row, if we look at it in the matrix form, it will also depend on the variable below, but only with one additional variable. Meaning it won't depend on y and z in this case. We don't know what y is, but we do know what z is because we have already solved for z. In short, there's only one unknown variable in this equation as well. And again, if we go up to the next equation, you'll see this depends on x, y, and z. We already know what z is because we calculated that earlier. We already know what y is because we calculated that earlier. We don't know what x is. So again, we have a system that only depends on one unknown variable, and we can rather easily isolate x. So we have turned the system of linear equations into a set of linear equations only dependent on one variable. And this is called back substitution. So we can take z, isolate for z, figure out it's 400 divided by 3. Middle equation, we just insert the z we figured out before and isolate to find y, 800 over 9. And in this case, again, we just insert x and y, isolate for x, 160 over 9. So for this system of linear equations, the results is x over 160 over 9, y 800 over 9, z 400 over 3. I hope you found this video useful. Thank you for watching, and I hope to see you next time.